Hello and welcome to the introductory video for the Western blot. In this short introduction I'll show you what is it and what is it used for. So to start off with, what is a Western blot? Well, essentially what we're doing, we are blotting proteins onto a nitrocellulose membrane to be read on a reader to see whether our protein of interest is there in our sample. So after blotting our proteins onto the membrane, we then apply a layer of primary antibodies. These antibodies are monoclonal mouse antibodies. So these are antibodies which are grown in a mouse which will target our specific protein of interest. We can then apply secondary antibodies. So these are rabbit anti-mouse antibodies which will only bind to the primary antibodies. And attached to these secondary antibodies, they have an enzyme called horseradish peroxidase attached to it, or HRP for short. And what this will do, this will catalyze a reaction of luminol into a compound called 3-aminophthalate, which is a fluorescent product. We could then enhance the fluorescence given by the 3-aminophthalate to allow us to analyze our results. So after doing all that, what is it used for? Well, it's mainly used for the detection and the identification of specific proteins in the sample. Moreover, you can then therefore look for the overexpression or the underexpression of that specific protein. And this application is quite commonly used in cancer research to identify specific proteins which cause, prevent or influence any tumorous growth. It's also used in research for Alzheimer's disease, and it's also being used for the diagnosis of Lyme disease, which can then be linked with an ELISA test, which stands for enzyme-linked immunosorbent assay. So during this short introductory video on the Western blot, I have covered what is it and what it's used for. I'm now going to continue on and show you the entire experimental procedure for the Western blot. So before you can begin the Western blot, there are a couple of preparatory steps you must do before you can do so. One of the first steps is to get some nitrocellulose membrane and to soak it in some methanol. What this does, it activates the membrane, allowing it to become more hydrophilic. You must also make sure you turn the membrane over, allowing both sides of the membrane to soak in the methanol. You then transfer the membrane and allow it to rinse in a small amount of water. And what this does, this will rinse off any excess methanol. Again, similarly to the first step, you must also make sure you turn the membrane over, allowing both sides to soak in the water. After rinsing off the membrane, you can then transfer it into a transfer buffer, and then it will sit in here until you're ready to continue the Western blot. So for this next step, you'll need 2 sponges, a blotting cassette, and you'll also need some blotting paper. Depending on the thickness of your blotting paper, it depends on how much you use. So in this video, we are using 2 pieces above and below for where we're going to sit the membrane. Then just to be tidy, you can fold up the cassette together and you can then place it in the module. What you can then do, you can then place the whole module into a gel tank. Then fill up the whole gel tank with some transfer buffer, allowing all of the module compartments to soak. So for the first step, you're going to need your polyacrylamide gel that you allow to go under electrophoresis, ensuring that the power supply is turned off. You can then remove the lid and then remove the cassette from within the chamber, remembering that there is running buffer within the reservoir, so make sure you pour this out before you move the cassette. You can then unclip the assembly and remove the polyacrylamide cassette from the assembly. If needs be, you can place the polyacrylamide into buffer while you tidy up the area around you. Now you are ready to begin assembling your blotting module, remembering to remove it from the transfer buffer that we have left it to soak in. So when assembling the blotting module, we always place things on the black side first. So to begin with, we place one of the sponges down, followed by two of our pieces of blotting paper. We must also ensure that the two pieces of blotting paper line up, as any lumps and bumps could interfere with the blotting process. The next step is to place our polyacrylamide gel on top of that. To remove the polyacrylamide from the plastic, you must carefully crack open the corners, ensuring that you do not break the polyacrylamide in the process. So once you've cracked open the plastic, you must then take care to notice where your polyacrylamide is. So after removing the first piece of plastic, you will notice that the polyacrylamide is actually stuck to the other piece of the plastic. And what we essentially want to do on the next step is to transfer the polyacrylamide onto the blotting paper. However, before we do so, we must remove any excess polyacrylamide. So this can even include removing the wells that are located at the top of the polyacrylamide, as again, any lumps and bumps could interfere with the blotting process. With the excess polyacrylamide removed, what you can then do, you can then place the cassette into some buffer to allow the polyacrylamide to loosen, making it easier to transfer onto the blotting paper.
This polyacrylamide gel should be placed on the black sheet and towards the cathode, and nitrocellulose membrane should be placed on the red side or white side, that is the anode, so that migration will be taking place from the protein will be migrating from the gel to the nitrocellulose membrane. This generally, if you put it on opposite direction, it will be wasted.
Usually the best way to transfer this over is to place the polyacrylamide face down onto the blotting paper, patting it down to remove any air bubbles, and then carefully removing the plastic.
The colors are markers.
So if you remember from the preparatory steps, we had the nitrocellulose membrane soaking in some transfer buffer. What we're then going to do, we are then going to remove the nitrocellulose membrane from the transfer buffer, and we are going to place it onto the polyacrylamide gel. So what you may notice is that when you lay down the membrane, you might notice some air bubbles forming. And one of the best ways to remove these is to pour some transfer buffer over it, and then using either a roller or carefully patting away the air bubbles. So with the air bubbles removed, you can then re-soak the blotting paper into some transfer buffer and carefully placing that on top of the nitrocellulose membrane. Similarly, you can then use one of the sponges, place that into some transfer buffer, and then placing that on top of the blotting paper. You can then close the blotting module and squeezing it to remove any excess fluid, and also ensuring that there is proper contact between the polyacrylamide gel and the nitrocellulose membrane. To seal the module, you then pull the white bridge over and clipping it into place. You are then ready to begin the transfer. So what you do, you bring over the blotting module and then placing the cassette into it, ensuring that the black side is facing the black side. So once the module is then into place, you can then place it into a gel loading tank. So with the assembly complete, you're going to add a magnetic stirrer and an ice pack to ensure that the whole module is kept cool, and you're then going to fill it up with transfer buffer. So after doing so, you can then place the lid back on, again ensuring that the red side goes to the red and black side goes to black. You can then place the whole module onto the magnetic stirrer until the transfer process is complete.
Even this magnetic stirrer will also help in maintaining the temperature also. Generally,
Power setting wise, the transfer process will occur at 115 volts. So once the transfer process is complete, you can then remove the lid and then remove the blotting module. If needs be, you can squeeze the module to remove any excess transfer buffer. You must then begin to carefully unclip the module. You can then place the module down, and if doing so, ensure that the black side is on the bottom. What you can then do is then remove each individual layer until you reach your nitrocellulose membrane. From here, you should be able to see whether your proteins are transferred successfully or not. You must then place the nitrocellulose membrane into some blocking solution. What this will do, this will prevent any non-specific binding from occurring later on in the process.
PBSA or casein will be using as a blocking agent. This is gel racker.
So the next sequence of steps is a rinse and repeat process, which will more easily be demonstrated via PowerPoint. These are the sequence of steps you do throughout the rinse and repeat process. And just so you're all aware, PBS stands for phosphate buffered saline. Okay, so the first step is to add blocking solution, and what this does, it prevents any non-specific binding happening between the antibodies and our nitrocellulose membrane. And the blocking solution consists of PBS with no fat milk. So imagine that this orange bar here is representing our nitrocellulose membrane, and these blue circles are representing our protein of interest. And this big green flood you see across here is our blocking solution. And this works by the proteins that you find naturally occurring in milk will literally just make a thin layer above the nitrocellulose membrane, preventing any of that non-specific binding from occurring. Okay, so the next step is to rinse with something called PBStween, and what this does, it removes any excess blocking solution. And all tween does, it promotes better washings when you're using it. So again, imagine here we've got our flooded nitrocellulose membrane with our proteins of interest, and as soon as we apply the PBStween, we're literally removing any of that excess blocking solution, leaving us with a thin layer. Okay, so now we are ready to add our primary antibodies. So these primary antibodies will only bind to our protein of interest. The antibodies we use are mouse monoclonal antibodies. So these are antibodies that were grown in a mouse which are specific to target these proteins. So we then flood our whole membrane with our primary antibodies. So after leaving these to settle for a while, we then need to remove any excess antibodies using PBStween. So we use PBStween and we wash, removing any of the excess. We need to do the process of adding antibodies and rinsing a total of 3 times. So you add antibody, rinse, add antibody, rinse, add antibody, rinse. So we're doing all of these steps in triplicates to ensure that all of the antibodies are successfully bound to our protein of interest. So once we have done the last step in triplicate, we are then ready to move on to add the secondary antibody. So the secondary antibody is an anti-mouse rabbit grown antibody, which is only specific to target these mouse antibodies. And attached to these antibodies, we have horseradish peroxidase attached. And what this will do, this will catalyze the reaction of luminol into 3-aminophthalate, which is a fluorescent product. So then after leaving the secondary antibodies to settle, we then need to rinse again with PBStween. And again, similarly to the previous steps, this will remove any excess secondary antibody. So it removes all the excess. And again, similarly to the primary antibody, we need to do this in triplicate. So we need to add the antibody, rinse, add the antibody, rinse, add the antibody, and rinse. Remember, everything done in triplicates to ensure all of the secondary antibodies have successfully bound to the mouse antibodies. So after we've done the final application of the secondary antibody and the final rinse using PBStween, we then need to do a complete final rinse using just PBS. What this does is this will remove any tween which has been left over, which can inhibit the detection process.
It inactivates enzyme activity basically.
So for the next step, we're going to need 2 reagents. We're going to need detection reagent 1, peroxide solution, and detection reagent 2, luminol enhancer. So here, measure out approximately 250 microliters of detection reagent 1 and pour this into a microcentrifuge tube. You are then going to need an equal volume of detection reagent 2 and then carefully mix these two reagents together in the microcentrifuge tube. What you then want to do is take your nitrocellulose membrane and place it onto a sheet of acetate. Then, using the solution of the combined detection reagents, carefully inject a layer of this over your nitrocellulose membrane, making sure that there is an even coating. Once you have successfully done this, place the second layer of acetate on top of the membrane, again ensuring that there are no air bubbles trapped within. Your membrane is now ready to be analysed, so open up the blotting reader and place your membrane onto the slot, and then reinsert it back into the reader. So depending on what blot reader you are using depends on what settings you need to use. However, for this one, all we need to do is switch it onto Western blot and it should be able to read it. If done successfully, this will be the final image produced.
Here, luminol is a fluorescence compound, so the sensitivity is very high. But in normal cases, the substrate what we use is TMB, tetramethyl benzidine. This in the presence of peroxide, peroxide releases free radicals, so peroxidase will cleave this substance and it will give brown to black color of substance wherever these secondary antibodies of HRP, horseradish peroxidase, are there. So in that case, whenever you are using TMB, then you need not to look under the UV like what this experiment has been seen. And you can see there are multiple bands. This is actually the darker bands are specific bands of your choice, like antigens of those proteins that we have targeted with antibodies. But there are some other bands also. You can see at the upper regions. See, they could be non-specific bindings or could be the dimers, tetramers, such kind of things. In such cases, there is a possibility of getting even positive, even in Western blotting technique.
As you can see on the image, any areas where you can see a dark band indicates an area of where you have